Okay. All right. Trinomials, that's three terms. Like this. X squared plus 2bx plus b squared. It's three terms. We want to factor that. Well, here are two perfect square versions. If you have x plus b and square that, then you have x squared. You have twice the product cross term, 2bx plus b squared. So if you had just ignoring these two, that x squared plus 2bx, want to know what to add to it to make it a perfect trinomial. Well, here's what you do to figure this out. If you have x squared plus 2bx plus b squared, you take this middle coefficient, divide by 2, that's b, it goes here. Square that, that's b squared, it goes here. And then that factors this. For example, x squared plus 9x plus 9, 6x plus 9. To factor that, we take half of 6, that's 3, and it goes here. Square that, it's 9, and it checks with that, so this works. So this will be x, so x squared plus 6x plus 9 will be the square of x plus 3. Similar thing, you have a negative sign in the middle. X squared minus 10x plus 25. Divide this minus 10 by 2, you get a negative 5. Put that there. Squared, it's 25, that checks against that. So x squared minus 10x plus 25 is the square of x minus 5. So for example, a squared plus 18a plus 21. Well, okay, half of 18 is 9, which goes there. Square that, you get 81, so it checks. So this thing equals the square of a plus 9. Now this one is a lot trickier. This trick here, which I call completing the square, doesn't quite work because there's a 4 in front of the y squared. So all you really need to know is it's square plus twice product plus square equals the square of a sum. So we have 4y squared plus 28y plus 49. If it's square plus twice product plus square, then it's the square of the sum. Let's see, 4y squared is the square of 2y. Good. 49 is the square of 7. Good. Now, if you have 2 times 2y times 7, that equals 28y, which it does, then this is the square of 2y plus 7, like that. Now, here's a more general problem. 1x squared, so it's best to have a 1 in front of the x squared, plus bx plus c. I want to be able to factor that into a product, x plus p times x plus q. Now, if you multiply it out, get x squared, fine, plus px plus qx, okay, it should equal bx, plus pq, it should equal c. So this will equal that if p plus q equals b and p times q equals c. So given b and c, you find p and q by searching the factors of c that sum to b. For example, x squared plus 5x plus 6. I want to find p and q, which product is c. So whatever p is, q is 6 over p. We go through various possibilities and then find out where the sum is correct. So if p is 1, let's try that. Then 6 over p is 7, and the sum is 7 is 6, and the sum is 7, which is not 5, no good. If p is 2, then 6 over p is 3, and 2 plus 3 is 5, and that does fit that. So this equals x plus 2 times x plus 3. Like that. T squared plus 14t plus 28. All right, we want to find p and q whose product is 48. We want their sum to be 14. Okay, pq is 48, so q is 48 over p. We'll try various values of p. And really, ultimately, there's no substitute for drawing this boring table, going through all the boring steps of checking every possibility. Some people say, well, we just sort of look at it and it comes to you in a flash of genius. I don't have time for that. So here's what we do. So we have p and 48 over p, and we want the sum to 14. Let's try it. P is 1, q is 48, the sum is 49, no good. If p is q, then 48 over p is 24, the sum is 26, all closer, but still no good. If p is 3, then 48 over 3 is 16, their sum is 19, we're getting closer. If p is 4, then 48 over p is 12, their sum is 16, oh, very close. And 5 doesn't work. 48, 5 doesn't go into 48. Let's try 6. 48 over 6 is 8. Their sum is 14. Yes. So this factors into x, t plus 6 times t plus 8. And there we are. Here we have a negative number. Things get a little gnarlier here, but not too gnarly. Want to know how to factor that? Well, their sum, P and Q, must be negative 17, watch out, and their product must be 72. So whatever P is, Q is 72 over P. All right, let's try 1. 72 over 1 is 72. The sum is 73, which is the wrong size and the wrong sign. But we can fix the sign. Let's try the negative numbers. Negative 1, 72 over negative 1 is negative 72. Sum is negative 73. Again, still wrong size, but at least it's the right sign. Let's try negative 2. 72 over negative 2 is negative 36. The sum is negative 38. Not there yet. Negative 4. 72 over negative 4 is negative 18. The sum is negative 22. It's getting closer. Let's try P is negative 6. 72 over negative 6 is negative 12. The sum is negative 18, almost. Let's try 7 doesn't work. 5 didn't work. 3 didn't work. But let's try 8. 8 works. 72 over negative 8 is a negative 9. The sum is negative 17. Bingo. So this factors into y minus 8 times y minus 9. Now it gets, let's make things a little harder. Before we had this previous method, which I call the PQ method, we had a 1x squared. Let's generalize it. Let's try an ax squared. Ax squared plus bx plus c, we want to factor that. Now here's the trick. We find a p and q, sort of like with the PQ method, such that the sum is b as before, and now their product PQ is not just c, but a times c. Therefore the name AC method. Then when you do that, once we have P and Q whose sum to B, then write this BX is PX plus QX. So AX squared plus BX plus C equals AX squared plus BX plus QX plus C. And this will factor by grouping, by unfoil. For example, 2x squared plus 5x plus 3. We want two numbers whose sum to 5, 2 and 3 do it, and their product is 2 times 3, 2 and 3 do it. 2 plus 3 is 5, 2 times 3 is 2 times 3. Good. So you rewrite this, write the 5x as 2x plus 3x. 2x squared plus 5x plus 3 is 2x squared plus 2x plus 3x plus 3. Now this will factor by grouping. First two terms are 2x squared plus 2x. Remove a factor of 2x, we're left with x plus 1. 3x plus 3 is a common factor of 3. Pull it out and we're left with an x plus 1. Now there's an x plus 1 in common, pull that out. X plus 1 times 2x plus 3. And there you go, we've factored this. Oh, before I go on, the reason why we're factoring is that we can solve equations. Namely, if this equals 0, then this product equals 0, and therefore one of these two factors is 0. And that's how you solve quadratics. We'll say more about this later. Now here I have a proof of why the AC method works. And I'll briefly go over it, and you can look at it again on the canvas if you wish. If you have two numbers P and Q which add to B and multiply to AC, then let's write Q as AC divided by P. That follows from this. Then AX squared plus BX plus C. We write the BX as PX plus QX. AX squared plus BX plus QX plus C. As QX, we write as AC over PX plus C, AX squared plus PX. Now I'm going to do a little tricky work. Write the C as CP divided by P. Then things happen because AX squared plus PX, the common factor of X, out it comes, times AX plus P. AC over PX plus CP over P, pull out a common factor of C over P, and we're left with AX plus P. And lo and behold, these are a common factor, pull it out, AX plus P times X plus C over P. So for example, and this is the sort of thing that makes more sense to actually do the routine until it gets easy to work with. See, 5x squared plus 13x plus 6. I want to factor that. And like I say later on, we'll see that it enables you to solve equations involving that. So you want to find P and Q, whose sum is 13, whose product is 5 times 6. That's 30. So all right, we have P, Q has to be 30 over P, and find out when the resulting sum is 13. If P is 1, Q is 30, the sum is 31, not quite. If P is Q is 2, then Q is 30 over 2 is 15, their sum is 17, closer but not quite. If P is 3, then Q is 30 over 3 is 10, and 3 and 10 makes 13, just right. So we rewrite this with a 13x as 3x plus 10x plus a 5x squared plus 6. The first two terms are 5x squared plus 3x. Out comes a common factor of x, times 5x plus 3 there. 10x plus 6 has a common factor of 2. Pull that out, times 5x plus 3. There that is. Now here's a 5x plus 3. Pull that out, times x plus 2. So there you are. X plus 2 times 5x plus 3. We factor this. 7a squared plus 12a plus 5 is what? We want to find P and Q, whose sum to 12. And this product is 7 times 5, that's 35. And okay, skipping a few steps, 7 and 5 work because their sum is 12 and their product's 35. So you write this 12a as 7a plus 5a, plus 7a squared plus 5. These first two terms are 7a squared plus 7a, common factor of 7a times a plus 1. 5a plus 5 is a common factor of 5. Pull that out, you get 5 times a plus 1. All right, common factor of a plus 1, out that comes, times 7a plus 5 here. So this factors into 7a plus 5 times a plus 1. All right, 7g squared minus 12gh minus 4h squared. All right, P plus Q should be equal to this middle term, coefficient, negative 12. P times Q should be 7 times negative 4, which is negative 28. So, okay, try various values of P, and Q is negative 28 over P. P is 1, Q is negative 28, the sum is negative 27, not quite. If P is 2, negative 28 over 2 is negative 14, the sum is 12, just right. So write this minus 12gh as 2gh minus 14gh, here and here. Now, factor by grouping. These first two terms are 7g squared plus 2gh. Common factor of g, pull it out. And so divide these by g, you get 7g plus 2h. Now, minus 14gh minus 4h. Well, obviously a factor of h, obvious factor of 2, and I'll make it a negative 2. So pull out a negative 2h. And when you divide these by negative 2h, we're left with 7g plus 2h. Now, okay, 7g plus 2h is a common factor. Pull it out. Times g minus 2h. And there we are. G minus 2h times 7g plus 2h. Now, here, okay, 64h to the 6th plus 24h to the 5th minus 4h to the 4th. Well, okay. Well, first of all, there's an h to the 4th factor in common. Let's pull that out right away. And 64, 24, and 4 are divisible by 4, so pull that out. And we divide each of these terms by 4h to the 4th. We're left with 16h to the 2nd plus 6h minus 1. Now this we have to use, is what we use the AC method on. We need a P and Q whose sum is 6, like this, and whose product is 16 times negative 1, which is a negative 16. All right. So whatever P is, Q is negative 16 over P. They want to find ones where P plus Q equals 6. If we let P equals 1, then Q is negative 16. The sum is negative 15. Wrong size and wrong sign. So we flip signs. P is negative 1, then Q is positive 16. The sum is positive 15. Still not the right size, but, right sign. Let's try -2 for p. Then q is -16 over -2, which is an 8. -2 plus 8 is a 6. Yes, as required. So let me write this 6h as minus 2h plus 8h. 4h to the fourth times 16h squared minus 2h plus 8h minus 1. Okay. We factor by grouping. Factor this and factor these. 16h squared minus 2h, well, is a common factor of h and also 2. So pull out a 2h. 16h squared over 2h is 8h. Minus 2h over 2h is -1. 2h times 8h minus 1. Oh, well, here's an 8h minus 1. That's one of those, 8h minus 1. Put a 1 there because otherwise it's invisible. 8h minus 1 common factor, pull it out, times 2h plus 1, there that is, times 4h to the fourth. And that's the answer. And yes, because I've seen people just write this, pull this 4h to the fourth, and then forget about it. No. Keep it along the whole time because we want the whole factorization at the end. 5x squared plus 4x plus 1. We want p and q to sum to 4, and its product is 5 times 1 is 5. Well, no matter how you try it, you get a 6, not a 4. So no factorization exists. This is a prime polynomial. It doesn't factor at all. And that happens, be advised. Don't give up too easily, though. All right, here we have 12y to the sixth plus 23y to the third plus 10. Now the sixth and third, oh, that's annoying. But really, this is just the square of y cubed. So treat it like a quadratic. Okay, we need p and q's sum is 23. This product is 12 times 10 is 120. So okay, whatever p is, q is 120 over p. I'm going to find how they sum to 23. If p is 1, q is 120, sums to 121, too big. If p is 2, then q is 60. 62 is the sum, too big. If p is 3, then 120 over 3 is 40. The sum is 43. Still not quite. If p is 4, then 120 over 4 is 30. The sum is 34. Still a ways to go. 5 works. 120, 5 goes into 120. 120 over 5 is 24. The sum is 29. Getting close. 6 works. 120 over 6 is 20. The sum is 26. Close. 7 doesn't go into 120, but 8 does. And 120 over 8 is 15, it turns out, and their sum is 23 as required. So there we go. So write this 23y to the third is 8y to the third plus 15y to the third from these. 12y to the sixth plus 8y to the third plus 15y to the third plus 10. Now these first two terms are 12y to the sixth plus 8y to the third. Common factor of y to the third and common factor of 4. So pull out 4y to the third. Then these divided by 4y to the third is 3y cubed plus 2. 15y cubed plus 10 has a common factor of 5. Divide these by 5 and we're left again with 3y cubed plus 2. So okay, pull out a common factor of 3y cubed plus 2 times a 4y cubed plus 5 here, and we factored the expression. Here we have a 28m to the 8th minus 60m to the 4th n plus 36m squared. Now, this is a square. 25m to the 8th is the square of 5m to the 4th. This 36n squared is the square of 6n. Now, if twice their product matches what we have in the middle, then we use the perfect square formulation. Let's see. 2 times 5m squared times 6n does indeed equal 60m to the 4th n. So we have square minus twice product plus square. That's a square of a difference. 5m to the 4th minus 6n all squared. All right.